So the whole theme of this section is how do we come to grips with linearized versions of exponential, logarithmic, and power function relationships. So starting from this graph on K1. So who worked on K1 yesterday? Do we have a group working on K1? Okay. So on this graph, we're relating the measurement of energy on a Richter scale to the amount of energy that was actually released by something, let's say a seismic event, which is usually what the Richter scale measures. So first of all, what equation can you give to this? What equation did you give to this linear relationship that's on this graph? Did you find one? So how can you find a linear equation, first of all, for this red line? So we have different scales going on. That's the theme of this section, is we have on the horizontal axis, we have a different kind of scale than we have on the vertical axis. What kind of scale do we have on the horizontal axis here, the Richter scale measurement? Linear or logarithmic? In the horizontal direction? Note that in the horizontal direction, between any two measurements that have the same difference between them, like 1 and 2 and 4 and 5, they have the same distance on this horizontal scale. So in the horizontal direction, we have a linear axis, because this is the usual kind of axis that you're used to working with in a graph. 1, 2, 3, 4, 5, 6, 7. It's characterized by equal differences corresponding to equal differences. Distances, differences. On the other hand, what's going on in the vertical axis?
Jumping by tens?
Yeah, it's jumping by tens, and when you say by tens, what operation are you talking about? Addition, subtraction, multiplication, division? Multiplication, right. So that's what makes the vertical scale a logarithmic scale, is that between equal distances on the vertical scale, we don't have equal differences, addition, subtraction, we have equal ratios, multiplication, division. So in the vertical direction, we have a logarithmic scale. In the horizontal direction, we have a linear scale. So here's my first question, and this can help you to navigate how to interpret these scales, both in the original fashion in which it's given to us and in a linearized fashion. How do you turn a logarithmic scale into a linear scale? What can I do to the numbers that are on the vertical axis to turn the scale from logarithmic into linear? How can we turn multiplication into addition? And or division into subtraction? The key word is already right up here on the board. What would happen? What would I see if I took the logarithm, the common logarithm, the base 10 logarithm of all the numbers that are on the vertical axis? Let's go one at a time here. Starting with what's the common logarithm, according to the work you did yesterday? What's the common log of the number 1? 0. So here what I'm doing is instead of plotting the energy itself, E, what I'm going to do is I'm going to plot log of E instead. Well, what just happened? So if we decide that we want to plot the log of E instead, the log of E, when E is equal to 1, is 0. What's the base 10 log of the number 10? 1. How about 100? 2. 1,000 is 10 to the power 3. 10,000 is 10 to the power 4, and so on and so on. So by taking the base 10 log of all of these numbers, I turn my logarithmic scale that I used to have into a scale which is now the kind that we're used to working with. 1, 2, 3, 4, etc., etc., etc. So after taking the base 10 log, now I get a scale that's linear, because equal distances correspond to equal differences. So I'm going to take the liberty, and this is actually usually, I think, the way that scientists depict a logarithmic scale. In particular, if you're working in the research group that's coming up with standards curves over and over again, this is probably what your standard curves axes look like, is instead of plotting the quantity you're interested in itself, you decide to plot the log of that quantity. So I'm just going to kind of erase what's on our vertical axis here. I'm going to try to keep my 1 just so I don't lose my place. And then instead of plotting E, we're going to decide to plot the log of E. And the log of E, if E had a logarithmic scale, the log of E has a linear scale. 4, 5, 0. Oh, sorry. So when we take the log of 1, we get 0. So our 0 point is right there. 1, 2, and so on and so on. So what this is saying is that on a plot of the horizontal variable r versus the vertical variable log of E, that graph is linear. That's the key observation. That's what we were, last time I was here, what we were talking about on Tuesday, was if we plot two transformed variables, one against the other, and we get something that's linear, then that should help us to understand what functional form, what equation, the original quantities satisfy. And we'll do that in just a second. So, what equation does R versus E look like? For the meantime, though, in addition to translating the numbers, the scale on the vertical axis, we should also take what used to be our y values for the marked points on here, and let's convert those also. We can't convert the scale that's on the vertical axis without also converting the y coordinates of the points. So how do I do that? In place of 2.0 in this point over here, what should I have instead? Yeah, I'm not really concerned about a decimal at this point. Let's just call it the base 10 log of the number 2. We can get a decimal for it later if we want to, but for now, we're just going to call it the base 10 log of 2. Likewise for 2,000. What replaces 2,000 in the y-coordinate at this point now that we've transformed our axis? Log base 10 of 2,000. So now not only have we transformed the axes, but we've transformed the y-coordinates of the points that are marked on this graph. And now those are points that lie on a linear graph. So now our job is to come up with an equation for this red line. But this red line is a line now. On a set of linearly scaled axes, it's just that one of those linearly scaled axes happens to be plotting a transformed version of the variable that we care about, E. We're plotting log of E instead, but let that go. We'll worry about that in a moment. So now we'd just like to find an equation for this red line. How would you like to do that? Yeah, Andrew.
You can start off with setting a y equals mx plus b.
Okay.
Log of b equals r plus b.
Yes. So let's first set up that linear functional form y equals mx plus b, just with the observation that the role of y is here being played by the log of e, and the role of x is being played by what?
R.
R. Right. So let's drop those in right away so we don't forget. So we're going to have an equation that looks like r equals m, some slope, times, oh, I'm sorry, I got this wrong already. Log of e, there we go. Log of e is equal to m times r, our independent variable, plus b. So that's what the equation is going to be telling us about e and r when we actually determine the two unknown parameters, the slope and the intercept. Now we just have to figure out what's the slope and what's the intercept. So first things first, how do we find what the slope of this red line is?
y2 minus y1 over x2 minus x1.
Yep, it's a slope. So we can find it the same way we find any slope, by dividing the difference in the y-coordinates of these 2 points by the difference in the x-coordinates between these 2 points. So y2 minus y1 over x2 minus x1. And y2 minus y1 is the base 10 log of 2,000 minus the base 10 log of 2. And the differences in the x's are 5 minus 3. Now, if you take the base 10 log of 2,000, and if you take the base 10 log of 2, you're going to get some nasty numbers. They're not very nice. But let's be efficient about this, maybe. Is there a way that I can simplify this expression, the log of 2,000? Can I make that expression look simpler? When we subtract one log from another, what are we really doing to its argument? If we're subtracting on the outside of a log, what are we really doing on the inside of that log? Dividing. This is one of the properties of logs that you looked at in the J problems yesterday. That division on the inside of logs is the same as subtraction on the outside. Why? Because a logarithm is an exponent. And when you divide powers, you subtract exponents. So when I subtract logs, subtract exponents if you like, I'm really dividing powers. Division on the inside of a log is the same as subtraction on the outside. And if you like that in formulaic fashion, the log of a quotient, a over b, is the difference of the logs, log a minus log b. But 2,000 over 2 happens to be a number whose common logarithm is pretty nice. What is the common log of 1,000? 3. So it turns out that the slope of this red line is not that nasty after all. The slope of this red line turns out to be 3/2. So we can just drop 3/2 right into our linear equation form. And we're halfway home toward finding an equation for this linear relationship. So let's talk intercept. Now that we know what m is, what are we going to have to do to find b?
Plug in the coordinates of a point.
Plug in the coordinates of a point. Which point?
Either or.
Either one, right. Either of the points that we know, if we plug in their coordinates into into r and to e, then we will get an equation which we can solve to determine the intercept. So let's do that step. Just because the numbers are a little smaller, maybe let's pick on this point. For this point, the value of r is 3.0. And the value of, this is interesting. How about this? The value of log of e is what? Is the log of 2. Right. After all, this log of 2 is our y value on our transformed axes. But y is equal to the log of e. So the log of e is equal to the log base 10 of 2. We could also just as well have gone back to the original coordinates of this point, because in the original coordinates for this point, we had a value for e, and the value for e was 2. So the log of e, therefore, must be the log of 2. So that's the only thing that looks a little different here, is that what we need to plug into this equation is not just an x and a y, if you like. Well, it is an x and a y, but in view of r and e, it's the value of r and the value of the log of e. But when I plug those in, on the left-hand side, I'm going to have log base 10 of 2. And on the right-hand side, I'm going to have 3/2 times r, and r was 3. Whoops. 3/2 times 3. Plus b, and b is what we don't know. And now, how do I solve this for b? So log of e is 3/2 r plus the log of 2 minus 9/2. So first, how can we interpret the slope of 3/2? So I'm going to take this number 3/2 out of here. And keeping in mind that anytime we're talking about a slope, we use words like increase. So this is an increase of 3 in one variable and an increase of 2 in some other quantity. But what are these increases in, really? Let's take the plus 2 in the bottom. What is this a plus 2 increase in? Which variable is increasing by 2 in this slope? Right. Keep in mind the denominator of a slope is always the run. And on our transformed axes, that horizontal axis is the Richter scale measurement. And I'll add one more clause here in the front. For each increase of 3 in something, there is an increase of 2 in the Richter scale. But now here comes the delicate part. What is this increase that we're talking about in the numerator? What's increasing by plus 3 if we're talking about the slope of our linearized graph? What was our vertical variable? Vertical quantity, rather. But it's not just the energy. In order to make this linear, we weren't using energy as our vertical quantity anymore. We were using its logarithm. So, in other words, we weren't talking, when we're talking about the slope of this equation being 3/2, the slope is 3/2 only when we plot r versus the logarithm of e, and not when we plot r versus e. So our slope was a relationship between r and log e, not between r and e. And so we have to, when we interpret this slope, take that into account. That every increase of 2 points on the Richter scale, so there's the denominator, every increase of 2 points on the Richter scale, corresponds to an increase of 3, not in the energy, so energy is not going up by 3 gigajoules, but instead the logarithm of the energy is going up by 3. What's another way to say that? It's increasing by 3 powers of...
By 3 powers of 3 magnitudes.
Yeah, any one of those I think would work. So let's think about what this might look like. So suppose on my vertical scale here, where I'm plotting the log of e, suppose that I take 3 steps upward, and each of those steps increases the log of e by 1. Well, when the log of e increases by 1, in other words, when our linearized scale increased by 1, what was our original scale doing? Mike, I think you were made this, or maybe no, Patrick made this observation. On our original scale, what was separating our tick marks? Not plus 1, but times 10. So in other words, every time the logarithm, the common log of a quantity increases by 1, the quantity itself increases by a factor of 10. When I say a factor of, that's what this little time sign there is an indicator of. A factor of 10. And so as Andrew says, the total increase that we see when we increase the log of e by 3, e itself increases by getting multiplied by 10 3 times. So I'm going to write that in symbols first. But when I multiply something by 10 3 times in a row, how much have I actually multiplied it by? 1,000, exactly, 10 to the 3rd power. So let's just write that as 1,000. And then just to finish making this into English instead of symbols, take the time sign away and write that it increases by a factor of. 1,000. So, all told, how we can interpret the slope of this linearized relationship is I'm just going to take this numerator, wipe it out, and rewrite it to say that for each increase in the energy released by a seismic event by a factor of 1,000, there is a corresponding 2-point increase on the Richter scale. There we go. Another way that we might say this is that if I have two earthquakes and one of them is 1,000 times more powerful than the other, then how much distance is going to separate them on the Richter scale? 2 points. If one is 1,000 times stronger than the other, then their Richter scale measurement difference is 2 points.